Hi class, this is Mr. Morris. I wanted to make a quick video on AP topic 4.2 net ionic equations. We've already kind of discussed this, but there are some important points that I want to fill in. So to get started with, let's talk about electrolytes and non-electrolytes. Electrolytes conduct electricity when they're dissolved in water, and the reason is because they dissociate into ions when they're dissolved in water. Strong electrolytes do this very strongly. They conduct electricity well because the compounds dissociate into ions completely 100% when they are dissolved in water. And weak electrolytes are pretty poor conductors of electricity because the compounds dissociate only partially in water. Really, it's like less than 5%. Non-electrolytes don't conduct electricity at all when they're dissolved in water because they don't dissociate into ions. So to give you kind of a context with a picture, this would be a strong acid, a strong electrolyte, because it dissociates completely. You can see that everything that's dissolved in here is an ion. And this one is a weak acid. It does not dissociate completely, so that's why you see the H plus ions, the HCO3 minus ions, but you also see H2CO3. It's not got a charge on it because it's still completely combined as an acid. So you've got a combination of dissociated ions and not dissociated ions. This over here is another diagram of kind of the same thing. You've got only ions in a strong electrolyte. As far as the solute goes, it's all ions. A weak electrolyte, the compound does not completely dissociate. Some of them do, but some of them are left together, as you see here. And then in a non-electrolyte, there's no dissociation that takes place. Strong electrolytes are soluble salts, strong acids, and strong bases. That's what makes up a strong electrolyte. Weak electrolytes are weak acids and weak bases, any that are not on the strong acid or base list, and we're going to talk about that in a moment. Non-electrolytes are polar covalent compounds like sugar or ethanol. So they're soluble in water, but they are covalent, so they don't dissolve, or they don't dissociate. They don't break apart into ions. Here are some things you want to put to memory. On the AP exam, this is what you will be expected to remember and to know as far as what dissolves, what dissociates. Your soluble salts, and by the way, when we say salt, we mean a ionic compound that is not an acid or a base. So it's an ionic compound. Your soluble salts are group 1 element salts like sodium and potassium. Also ammonium salts, so if it starts with NH4, and nitrate salts, so if it ends in NO3. Those are the ionic compounds. You really need to know that any ionic compound that is made with a sodium, potassium, or ammonium ion, or a nitrate ion, are always going to be soluble when they're dissolved in water, and there are no exceptions. That's really what the College Board curriculum is going to be testing you on. There are other rules we'll talk about too. Strong acids and strong bases that you need to memorize. This is the list of the strong acids. This is the list of the strong bases. And anything that's not on that list, any other acids and bases are going to be weak acids, weak bases. I can give you some tips on how to remember these, but really it's probably a good idea to just kind of put them to memory. HCl, HBr, HI, HNO3, H2SO4, and HClO4. Those are strong acids. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and hypochlorous acid. Hypochlorous acid, sorry. And then your strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, all of them that are group 1. And then you've got CaOH2, SrOH2, and BaOH2. Here are the solubility rules. Really, the dividing line between soluble or insoluble is about 0.1 molar at 25 degrees Celsius. Any substance that can form 0.1 molar or concentrate or more concentrated is defined to be soluble, and any substance that fails to reach 0.1 molar is defined to be insoluble. So if you are able to dissolve 0.1 molar or more in solution, it is a soluble substance. If not, it's insoluble by our somewhat vague definition. The value was picked with a purpose because there are very few substances that have a solubility, a maximum solubility, that is near 0.1 molar. Almost every substance that's important to chemistry is either much more soluble or less soluble than that number. Here are solubility rules. You may want to refer back to them as you go through the notes. As I said, the couple rules listed on the last slide are the ones that you'll be expected to remember, along with strong acids and strong bases. However, here are some rules that are a good idea to put to memory as far as ionic compounds dissolving in substances. These are good to, you're going to need to use them as you're working through the practice. And basically the way that this chart will work, compounds containing these ions are going to be soluble. The exceptions over here will tell you in which case that is not true. So when an ionic compound is made with chloride, bromide, or iodide, but they're paired up with these ions, they're insoluble. But with anything else, they're going to be soluble. Sulfate has a couple exceptions. And then down here in the second part of the table, these are the ones that are usually insoluble, and our exceptions would tell us with certain things they're actually soluble. So let's look at representations of strong electrolytes in aqueous solution. This will lead us into doing net ionic equations. All strong electrolytes dissociate completely into their ions in water. In a complete ionic or net ionic equation, all strong electrolytes are always going to be represented as ions. So let's do some examples. First, we need to decide, is it a strong electrolyte or not? If it is, then it's going to be represented as ions. If it is not, it will be represented in the exact same form that we see it written in over here in the first column. Let's start with KBr. Well, KBr is it's an alkali metal, so that means it's going to dissolve in water. It's a salt that will dissolve in water, so yes, it is a soluble salt. It is a strong electrolyte. Lithium is also an alkali metal, group 1, so this is going to be a strong electrolyte. PbSO4, well, that's a sulfate. Sulfates are usually soluble, but there are some exceptions. Lead is one that comes up a lot. So Pb, just watch out for Pb on the AP exam. If you see Pb bonded with something other than nitrate, it is probably insoluble, as is the case here. It's an insoluble salt. HNO3, well, that is a strong acid, so yes, it is a strong electrolyte. HF, starting with H again, so that is an acid, but is it a strong acid? It is not on our list of strong acids, so no, it's a weak acid, it's not a strong electrolyte. Then we have BaOH2. Is that a strong electrolyte? It is, because it's one of our strong bases. But then we have FeOH3. It's a base, but that's a weak base. So no, it's not a strong electrolyte. CH3OH, that is a non-electrolyte. Looks like a covalent compound of some sort. That's an alcohol, actually. C3H6O, again, that's a non-electrolyte. Then I have Na2S2O3. We may not be familiar with that, but I see that it's a metal and it looks like a polyatomic ion. So that's an ionic salt. Question is, will it dissolve? And since sodium we know is a group 1 metal, yes, it's a strong electrolyte. It's a soluble salt. KHCO3, same thing. It's going to be a soluble salt. NH4, CH3COO, that's also going to be a soluble salt, and NH4 compounds, they're always going to be soluble. So yeah, that will dissociate. CH3COOH. Well, this is actually a weak acid. I wouldn't necessarily expect you to know that by now, but it is definitely not going to be a strong electrolyte. It's a weak acid. And then K2HPO4, yes, that's a soluble salt. So how do we represent these in an ionic chemical equations? Well, look at KBr, for example. It's going to dissociate completely because it's a strong electrolyte. Well, it's going to break up into its ions. I have one potassium ion, one bromide ion. So my representation would look something like this. K plus Br minus. Over here, this one's also going to split apart. But I have 2 lithium ions because I have a subscript of 2. And then CO3 is a polyatomic ion with a -2 charge. So I'm going to have 2 lithium ions and 1 carbonate ion. Now I have PbSO4. Well, it's an insoluble salt, so it's just going to look exactly like it does over here. We didn't change it at all because it is not a strong electrolyte. Okay, this one's a strong electrolyte. I'm going to break it apart into its ions, H plus and NO3 minus. This one is not a strong electrolyte, so it just stays HF. I have a strong base here, so I have Ba2 plus and 2 hydroxide ions. FeOH3 is a weak base, it stays the same. This one also is a non-electrolyte, it stays the same. This is a non-electrolyte, it stays the same. This soluble salt will break apart into its ions, so I have 2 sodium ions, 2 Na plus ions, and then I have one of these ions, S2O3, with a -2 charge. Then I have KHCO3, yes, it's a soluble salt, so K plus and HCO3 minus. NH4 plus and CH3COO minus, that's acetate, by the way. And then this one is just going to stay the same because it's a weak acid. And then finally, 2 K pluses. I have 2 potassium ions and HPO4 with a -2 charge. Now let's apply this to some chemical equations. There are types of chemical equations that we're going to talk about today. This is really only applicable when there are aqueous reactants and or products. We don't have to worry about it if they're not aqueous. So we have the complete balanced equation. That's what we're used to writing. It gives the overall reaction stoichiometry, but not the forms of the reactants and products as they exist in aqueous solution. Then you've got your complete ionic equation. That represents all of the reactants and products that are strong electrolytes as ions, and we just talked about what strong electrolytes are. But the net ionic equation includes only those solution components undergoing a change. The spectator ions are not included, and when we say spectator ions, that means any ion that does not undergo some sort of change. In other words, it doesn't change its charge. It does not combine with another ion to form a compound or anything like that. Spectator ions are not involved in the reaction process. It starts and finishes as the same ion. A little hint for you, since electrolytes only ionize in water, pay attention to AQ in equations. Then only ionize strong acids, strong bases, and soluble salts. We're going to use that quite a bit. Strong acids, strong bases, soluble salts. We'll represent those with these letters, SA, SB, and SS. Let's look at our first example. All right, I have a solid. I have a solid here, I have a gas here, and I have a gas here. I don't see anything that's aqueous, so that doesn't really apply. If I were asked to write the net ionic equation for this, the answer would be exactly the same as what I just wrote. There's no AQ, so the net ionic equation equals the complete balanced equation. Just rewrite it the same way. That one was almost too easy. Let's look at another one. We have aluminum as a solid. Now we have an aqueous CuCl2 solution. I have a solution of AlCl3, an aqueous solution, and then 3 copper solid. So what I want to do is first think about how these are going to break apart. What is going to break apart? Well, this is a soluble salt. This is also a soluble salt. So those are going to dissociate into their ions. So I'm going to end up with 3 copper 2+ ions. And because I have 2 chlorides for every copper chloride, I'm going to multiply 3 by 2 to find out how many chloride ions I'm going to get. 3 times 2 is 6. So 6 chloride ions, that's Cl-. Okay. So let's take a look at what we get. Aluminum stays the same because it's a solid. Then I have 3 Cu2+, as I just said, 6 Cl-, like we just said. Over here I have 2 aluminum ions, 2 Al3+. 2 times 3 gives me 6 chloride ions, 6 Cl-. And then finally I get 3 coppers that are still solid. By the way, I usually eliminate the states of matter here. I guess I missed a couple of them, but you can eliminate the states of matter in this middle step just so you have less to work around. The next thing we want to do is make the net ionic equation, which is made by canceling out anything that didn't change. And we're talking about changing charge or other form. So I have aluminum as a solid over here, but it turns into aluminum 3+ over here. That's a change. I can't cancel that out. I have 3 Cu2+ on the left. On the right, I have 3 Cu, no charge. It's now a solid. I cannot cancel that out. But then I see 6 Cl-, and I also see 6 Cl- over here. So we can cancel those out. And when we rewrite the equation, the net ionic equation, we write everything except chloride in the equation. That is our net ionic equation. We've eliminated the spectator ion, which was chloride. Spectator ion was chloride. This is a longer equation, a lot more going on. So let's break it down. HCl is a strong acid that would dissociate completely. H2C2O4, that's an acid, but it is not a strong acid. It's not on our list that we are going to memorize with strong acids and bases. This one is a salt. It's a sodium salt, so that's going to be a soluble salt, and also you can look at the state of matter here, aqueous. Okay, manganese chloride, that's aqueous, so that's a soluble salt. Sodium chloride it's aqueous, that's a soluble salt, and then everything else is going to stay intact. So the weak acid, it's going to stay intact. We're not going to dissociate that because it is not strong acid or a strong salt or a strong base. Let's look at what we get when we break these apart. We have 6H plus, 6Cl minus. We have 5 of the weak acid that we have here. We have 2Na plus, 2MnO4 minus. We have 2Mn plus. We have 4Cl minus. That's 2 times 2. That's where that came from. I have 2Na plus. I have 2Cl minus. I have 8H2O and 10CO2. It's a lot to write down in this first step. Now let's start canceling things out. First thing I see is H plus. Let's see if I see H plus on the other side. I don't see it in that same form. 6Cl minus. Well, I see 6Cl minus over here. I see 4 here and 2 there. Well, 4 plus 2 gives me 6. So yes, Cl minus is one of our spectator ions. Okay. This is not an ion, so that's not going to be a spectator. I have 2Na plus over here, and there it is, 2Na plus on the other side. And then finally, my MnO4, I do not see it on the other side. We're done canceling things out. Now we just rewrite the equation, leaving off the spectator ions. And again, our spectator ions are chloride and sodium. 2HNO3 plus CaCO3. Well, let's look at it. This is our aqueous, one of the aqueous solutions. HNO3 is a strong acid, so that would dissociate. CaNO3 well, that's going to be a soluble salt, so it would also dissociate. Everything else is solid, liquid, or gas, so we're not going to worry about breaking those apart. So we're going to get 2 H pluses, 2 nitrate ions. This will stay intact. This will break up into 1 calcium 2 plus ion and 2 nitrate ions. So that's what we end up with. H plus is not found on both sides. I have 2 nitrate ions on the left. I have 2 nitrate ions on the product side, so those can cancel out as spectator ions. And then CaCO3 breaks apart into calcium and these other components. All right, let's rewrite it without the spectator ion, which was nitrate. So we have 2H plus CaCO3 yields Ca2 plus H2O plus CO2. All right, I have FeOH3 as a solid, 3 HC2H3O2 AQ. Okay, that is an acid, but it's a weak acid. Then I have FeC2H3O2 aqueous. Well, that's a soluble salt, so this will dissociate, but that's the only thing that dissociates. The weak acid will not. So let's write it out. Now I'm going to look for spectator ions. Well, there are actually no ions on the left side of the equation, so there are no spectator ions. If there are no spectator ions, the net ionic equation is the same as the complete balanced equation. And that's what we have right here. Well, the complete ionic equation, I should say. It's the same as the complete ionic equation, which is what we have written here. All right. Ki, NaCl, KCl, NaI. All of these are soluble salts, so they will all dissociate. I have K plus, I minus, Na plus, Cl minus yields K plus K plus Cl minus plus Na plus I minus. Let's start canceling things out. Do I see K plus on both sides? Yes, I do. Do I see I minus on both sides? Yes. Na plus? Yes. Cl minus? Yes, I do. Well, everything just canceled out. So there is no reaction. If all the species are spectator ions, there is no reaction. Now we have bromine plus potassium iodide yields potassium bromide and iodine gas. Start out by looking at our aqueous solutions. Are they electrolytes? Are they strong electrolytes? Well, they're both soluble salts, so yes, they are. We'll break those apart. We have Br2 plus 2Ki, so 2K plus 2I minus, and then on the other side we're going to have 2K plus and 2Br minus, and then the iodine. Now let's cancel out our spectator ions. Well, bromine is definitely not a spectator. We have 2K plus on both sides. That's our spectator. 2I minus here, but it turns into iodine as an element on the other side. That's not a spectator. Get rid of the K plus. Bromine plus 2 iodide yields 2 bromide plus iodine. K plus is the spectator ion. All right, that's it for our notes on net ionic equations. I hope that's helpful. Maybe try your hand at the practice and let me know if you have any questions.